Hello everyone, welcome to my channel Chemistry by ANR. In today's session, we are going to deal about fructose, which is a ketohexose. What is the structure of fructose? How can we say that the anomeric carbon of fructose is at carbon number 2 and the anomeric carbon of glucose is at carbon number 1? What is the Havoth representation? What is the Fisher projection? All these things we are going to deal with. Hello everyone. Let us discuss about fructose, which is a ketohexose. That means it has a keto linkage with 6 carbon atoms in total. The keto linkage is at C2 and carbon number 2 is considered to be the anomeric carbon for fructose. Fructose and glucose is obtained by the hydrolysis of sucrose, and that we have already seen in the previous module. Now, it is very important to understand that apart from the structures of carbon number 1 and 2, rest of the carbon, C3, 4, 5 and 6 of fructose is same as that of glucose. This is the structure of fructose which you can see over here, and if you can recall the structure of glucose, it was something like this. It was CHOH over here, and then rest is what? Rest is CHOH whole thrice and CH2OH. So carbon number 1 in glucose was anomeric carbon. Carbon number 6 was having a 1 degree alcoholic OH, and the structure over here as per Fisher projection was like this. So this is CH2OH, and in between it was C2, 3, 4 and 5. Remember 21, 22 in the previous module I have already said 2 is OH, 1 is H. So 2, 1, 2 and 2. This is the configuration of the right hand side. This is the configuration of the right hand side, and accordingly it is H, OH, H and H, and this is for D plus glucose. Now, if it is D plus glucose, the open chain structure, we can see that configuration from C3 to C6, 3, 4, 5 and 6 is same as in fructose. So glucose and fructose, they differ only at C1 and C2. And remember that this fructose is again a compound that belongs to the D series. Why it is D series? Because the lowest asymmetric carbon or the last chiral carbon, that is C5, this is the last chiral carbon or lowest asymmetric carbon that has a configuration similar to that of D plus glyceraldehyde with OH group on the right hand side. So in D plus glyceraldehyde it was like this. It is CH2OH, and here it is OH and here it is H. So this is the chiral carbon. And in fructose, you can see that the last chiral carbon is having OH on the right hand side, and hence it belongs to the D series, D configuration. And point to note over here is fructose has a levo-rotation. It shows a levo-rotation. So its optical activity is L or minus. So never write small d for configuration. Capital D is always configuration. Small d is always optical rotation. So for minus, you can also say this is L. That means levo-rotatory. Now, it also exists in two cyclic forms as you have seen in glucose. That is alpha form and the beta form. How did you obtain this cyclic form? Let us see that again as we have seen in glucose. Let us see. So for fructose, it is like this. Carbon number 1 is a CH2OH. Carbon number 2 is C double bonded O, which is a keto linkage, and it is carbon number 2, the anomeric carbon. Rest of the structure is like this. CH2OH in C6, this is C3, 4 and 5. So it was 2, 1, 2 and 2. So we can see that here in C5, what happens is the lone pair above oxygen. So this is OH, H and H. The lone pair above oxygen will attack the anomeric carbon, which is electrophilic in nature. O opens as O minus and it will hold this H, forming OH. So what configuration you are getting over here is there are two cyclic forms. This is the C2. So if I write carbon number 2, this was a chiral, was not chiral because it was having double bonded O. Now it becomes chiral. In one configuration, it can have OH on the right hand side. This is C2. On the left hand side, it is a CH2OH. This is C1. And rest of the carbon will be like this. CH2OH. This is 3, 4 and 5. C2 and C5 is held by oxide linkage like this. And rest of the structure of C3, C4 remains unaltered. It is like this. So this is the cyclic structure where we can see that the OH is on the right hand side at anomeric carbon, which is carbon number 2. This is the anomeric carbon. And hence you say that this is the alpha form. So this is alpha D. Why? Because it's D series minus. Now fructose, the cyclic structure, the hemiacetal form is containing 1, 2, 3, 4 and 5 member including oxygen whose structure is similar to that of furan. So the name is furanose. So I will say this is alpha D minus fructofuranose. Fructofuranose. So this is the cyclic structure of fructose. Now over here, please remember that if the OH of the anomeric carbon, if the OH of the anomeric carbon is on the left hand side, like this, OH, this is your C2 and here it is CH2OH, C1 and same thing, here it is a CH2OH, C6, 3, 4 and 5. So whatever was here, it's the same, H, OH and there is an oxide linkage between C2 and C5. So this is OH, this is H and this is H. So since here the OH is on the left hand side at the anomeric carbon, carbon number 2, the name for this cyclic form of fructose will be beta D minus fructofuranose. Fructofuranose, because the ring is having 5 member including oxygen, same as that of the heterocyclic compound furan. Similarly, you can draw the Haworth structure. These are the Haworth structures. This is your Fischer representation. So this is your Fischer structure. In the Haworth structure, always remember that the oxide linkage is between C2 and C5. So first you have to make this part clear, how to draw the Haworth structure. So you said that, okay, this is between C2 and C5. Fine. So now you will draw this oxide linkage in this manner. Mark this as 2, mark this as 5. Remember C5 will have a CH2OH, which is carbon number 6 and H here. And this is 2, 3, 4. And always remember that Groups on the right hand side in the Fisher projection will be below the plane in the Haworth structure. This I have told you in the previous module. So in the Fisher structure, whatever group is on the right hand side in the Haworth structure, those groups will be below the plane. So if I want to represent the alpha form, alpha D minus fructofuranose, the configuration at C2 on the right hand side is OH. So this is OH. And what is on the left hand side is a CH2OH. So this is your carbon number 1. And it is H and OH. So here it will be OH, here it is H. So mark with what you have in the book. Please always remember, as you are seeing the module, try to draw the structures along with me in order to learn better, in order to understand and remember. So this is how you have drawn the alpha form. So you should keep in mind, for the beta form, only the configuration at C2 will change. OH will go above the plane and CH2OH will come below the plane. Rest of the thing will be remaining the same. Just see what has happened here. So this is the Haworth structure, and these are the two anomeric forms of fructose. Now, there is an important question which comes often in your board exam. You are told to explain the fact that glucose and fructose, they often produce the same osazone. This is known as osazone, which is obtained by the reaction of C6H5NH2, phenylhydrazine. The name is phenylhydrazine. So by the reaction of glucose with phenylhydrazine or fructose with phenylhydrazine, you see that the configuration at C1 and C2 is the same, whether you start from glucose and obtain glucosazone, or you start from fructose and you obtain fructosazone, because it is by the removal of H2O that you obtain CH double bond NNHC6H5. And over here again, remember that it is again like removal of H2O in order to obtain this configuration. So the configuration at C1 and C2 in the osazone remains the same whether you start from glucose or you start from fructose. So you get the same structure of glucosazone and fructosazone. Moreover, structure of C5, rather C3 to C6 is remaining the same for glucose and fructose. So what will be your answer? Your answer will be that osazone formation involves C1 and C2, where the product has this structure. In the structure of glucose and fructose, C1 and C2 only differs. Rest of the structure, C5 to C6, is the same. And since in osazone, C1, C2 structure is same for glucose and fructose give same osazone with phenylhydrazine. And you have to give this particular chemical reaction. You may not remember whatever things are eliminated, but you have to remember the structure of phenylhydrazine, structure of glucose, fructose, and the osazone. So that's all for this session. We are going to deal with disaccharides in the next module. Till then, bye all of you.